Okay, so let me welcome you to the Global Network Forum on Climate Change. We heard this, I learned this morning, it's obviously then the second most important panel we have, because there was already a plenary on a similar topic. And just to diversify a little bit, I mean, it's clear that there will be some overlap, but we try to bring a little bit the idea of young generation and also of the question and concerns of the young generation into this round. And therefore, I'm very happy that for the panel today, I have two representatives of the young generation here. They are an example of two girls here, thinking a little bit outside of the box, moving around in Europe in their education and really looking into different matters from different sides. So on one side, it's Dr. Charlotte Bewick. She's with OHB since 2012 as a system engineer. She works in the Earth Observation Group, so the right topic. And she is working in the Copernicus program, so on the running LSTM, so this is a surface temperature monitoring study, and there's a phase AB1. She had a PhD from University of Strathclyde, and she received a couple of medals and already prizes in international area, so she's really a little bit a bird flying a little bit around and looking here and there, and then also doing obviously a good work. Then I have a second lady here on the floor. That's Audrey Backwand. So she's also with the University of Strathclyde, and she's working there in the Intelligent Computation Engineering area, IAC. She has a Master of Science from the Aerospace Engineering from KTH, the Royal Institute of Technology in Sweden. And before joining the ICE, she worked 3 years for the Earth Observation Future Mission at Aztec. So there's also a touching point into the topic here. And then I'm also happy to have two seniors here on the floor. To the right-hand side here, I have Professor John Burroughs. He's from the University of Bremen, so he's director of the Institute of Environmental Physics and Remote Sensing, and he's a professor on the physics, ocean, and atmosphere. And the second colleague here, who was already also sitting this morning on the panel, it's Dr. Michael Freilich. So he's director of Earth Science Division in NASA. So highly relevant to the topic. And we thought a little bit this discussion today, we start with two impulse talks from the senior participants, and then we go on a little bit into a discussion, piling up and basing also on this morning discussion, where a lot of interesting conclusions have been generated. But I think let's see how it goes. And I also would want to encourage my two young generation ladies on the floor really to get also with questions into this discussion. But maybe Michael, you can start a little bit and just give us within an impulse talk a good basis for this discussion.
Sure, thanks very much, and thanks for everybody coming here. Being from NASA, of course, I have some view graphs, but it occurs to me that this panel is incredibly bimodal, not only gender-wise, but age-wise. I guess that was the idea. Half of us, are wondering what it will be like when we're 50, and the other half of us are trying to remember what it was like when we were 50. Anyway,
it's involving everyone, Michael. That's
if we could have the first slide, please, and the next one, please. So, I'd like to talk to you to get this started, to have a conversation a little bit, not just focused on greenhouse gases, but actually on the changing climate. Because the climate is changing, and we have a remarkable responsibility as the only species that can look ahead to future generations and change what we are doing now based on our projections of that. That is a huge responsibility that we have, and we have a tremendous technical expertise to know that the climate is changing. From the vantage point of space, there are a number of clear signs. One of them is, and I use this all the time when people question the issue of changing climate. One of them is sea level rise. Why is the ocean rising? And from the vantage point of space, we know with precision and accuracy that in a global mean sense, sea level is rising, what, 3.2 millimeters per year, plus or minus 0.4 millimeters. And by making precision gravity measurements as well, we know why, in the sense, or what the components of the sea level rise are. Because by measuring the amount of mass that's put into the ocean, we know that that amount from melting water on the land only accounts for about 1.8 millimeters per year of the sea level rise. And the bottom line is that the difference is thermal expansion of the oceans. Next, please. We also know from the vantage point of space that ice is changing. From satellites, we know not only that the sea ice in the Arctic, the area of the sea ice, is decreasing, but we also know from these thumbnails, as you can see, that the ice itself is thinning. The red in the thumbnails is thick multi-year ice, which is modulated by ocean phenomena, and the blue areas are thin first-year ice, which are modulated by clouds, basically, solar insolation. And it's the sort of change in modulation mechanisms between, say, an oceanic mechanism and an atmospheric mechanism that can really cause tipping points or rapid changes in the climate. Next, please. If you can start the animation on this. Whoops. Okay, sorry, I forgot to set this up. Let's go to the next one. Carbon dioxide in the atmosphere is increasing. You know that. Greenhouse gases are causing our planet to warm. And humans have added a tremendous amount of carbon to the atmosphere. And we know that on a decadal sort of time scale, about half of the anthropogenic carbon stays in the atmosphere. The other half goes from the land, or goes into the land or into the ocean. We're not exactly sure of that partitioning, and we're rather uncertain about the mechanisms. And the year-to-year variability is huge. Some years, as you can see in the plot on the right here, some years almost all of the anthropogenic carbon stays in the atmosphere, and some years almost none of it stays in the atmosphere. Understanding the natural air-sea and air-land processes which control the fluxes of carbon is critical if we are to understand how the planet will respond into the future, and especially under different climate conditions. And it's that question, understanding the natural distributed sources and sinks of carbon and the modulation processes, that is driving NASA's remote sensing for carbon dioxide and other greenhouse gases. Next, please. With the launch of the Orbiting Carbon Observatory 2 to make global measurements of, with quite high precision and relatively good accuracy, of CO2 mixing ratios in the atmosphere, we can actually see the Earth breathe. If you follow this time series of sort of 2-week concentrations of carbon dioxide from spring through summer, you can see that the northern hemisphere carbon dioxide levels are very high as we go into spring. Photosynthesis is not yet effective to scavenge carbon dioxide to the land, and there's a lot of CO2 from the winter from fossil fuel burning. But as time goes on, we can see that the photosynthesis in the north cuts in, and virtually all of that additional carbon dioxide is scavenged to the land temporarily. Next, please. NASA has a number of different CO2 measuring instruments that are flying and that will fly. And hopefully, as in our discussions, we'll be able to talk a little bit more about it. Right now, the Orbiting Carbon Observatory 2, since July of 2014, is flying and has been making measurements. It made very interesting measurements, by the way, through the 2015-2016 El Nino, where unprecedented amounts of CO2 were put into the atmosphere, and we understand why. It was mostly from southern hemisphere, from equatorial tropical forests, but the mechanisms for the change are quite different in the three basic geographical areas. OCO3, which is an instrument that was actually made from spare parts of OCO2. When we started that program, I told the President's science advisor that we were going to robustly spare it and possibly be able to make a second instrument, and indeed we have. And it's scheduled to launch in February timeframe to the International Space Station. Coupled with OCO2 and with the Japanese GOSAT and GOSAT-2, we will have many more precision measurements of CO2 in the atmosphere than we've had previously. The interesting thing about the space station is that since it is not in a sun-synchronous orbit, we can use those measurements to actually, over time, probe and illuminate the diurnal cycle. Whereas in a sun-synchronous orbit, the satellite is always passing over the same place at the same local time. And finally, in the 2022 time frame, using the same basic measurement approach, we will be making measurements of CO2, carbon monoxide, methane, CH4, and solar-induced fluorescence from geostationary orbit with the GeoCarb mission, whose PI is Berrien Moore. This will be a technological revolution because it will allow us to make relatively high spatial resolution but extremely high frequency in time measurements over North America and South America and Central America. And one can conceive of a future constellation of geostationary CO2 and other greenhouse gas measuring instruments similar to the geostationary meteorological satellites that we have now for measuring atmospheric dynamics and thermodynamics. So this is a very brief overview, hopefully to generate some questions of what we know and where NASA is going in terms of greenhouse gas measurements from space. Thank you.
Oh, thank you very much, Michael, for that first surf in this direction. And I think it's obvious. I mean, the temperature changes, the sea level rises, and it's obviously also important not only to measure CO2 but also a total mixture of gases you just mentioned. So, but it's good to see that there's a lot of sensors already available, and there's more to come also in the Copernicus program when Europe jumps in, maybe a little bit later here in 2020, starting from there. But the things do develop there. Okay, so then the next impulse comes from the science side, from the university. I'd like to ask Professor John Burris to give us an insight.
Thank you very much indeed, Timo. Thank you, Michael. That was a great talk. Okay, so I'm going to, I actually quite nicely, we haven't really done this, but I think I quite nicely complement Michael's talk, because I'm going to talk a bit about how we measure it and what kind of measurements we need to be fit for purpose. There's an element always in space that we have to do technological development to be able to do things, but there's also an aspect of space which is delivering evidence, delivering services for people that are really needed, and that's what we're pushing towards. Now, it happens that we're trying to understand the impact of man, in particular for climate change, on the carbon cycle. Michael showed very nicely different aspects of climate change, obviously temperature change, but we think this is being driven, and we have been thinking this since Arrhenius around 1900 did back-of-the-envelope calculations which said CO2 would actually increase, a doubling of CO2 would be about a 4-degree increase. Now, over 100 years later, actually it's about the same. So the basic of the physics is sort of the same. Obviously our knowledge of it, and the issue is also nowadays the regional change. Actually Arrhenius thought that heating up, living in Scandinavia, he thought heating up might be not so bad. So we have to understand this cycle, which is complex, is what I want to say, and there's lots of elements to it and the carbon moving around. But particularly important players in the carbon cycle are CO2 and methane, because of they're the two most important greenhouse gases being modified by man. The next is nitrous oxide, but I'm going to focus on talking about the ability to measure and see changes in CO2 from space. There are extremely good measurements on the ground, but they are intrinsically limited by being sparse. The advantage of space is that you fill the gaps, but it's a tough challenge for our engineers and our scientists to build the instruments. So how do we do this? And this is a story that began in Bremen, or even a little bit before when I was in Mainz, because an instrument called SkyMatchy proposed to use for the first time the shortwave infrared CO2 fingerprint absorptions coupled with oxygen. And here are some examples of the spectra. For those of you who don't know too much about spectroscopy, these are like fingerprints of the molecules, and in terms of absorption, they increase. And we look at the reflected. So this is a sunlight measurement, a daytime measurement, and we're looking essentially between the clouds. And then we use what's called differential absorption spectroscopy to determine the concentration. Okay? We also have to assess the light path, and we have to deal with scattering, because we need a very precise measurement. We have to measure 400 ppm nowadays of CO2, plus or minus, hopefully, maybe 0.1 ppm. Those are the type of things we need to do. How do we do this? We go from the measurement, then we want to have to calculate the emissions. For that, we need to understand the wind, and we need to sample rapidly enough to be able to do this. So you get the CO2 in the air parcel, or the methane, and then you look at how it's changing, how you see the plume. It's like looking at a plume of smoke coming out a chimney, in principle. But we have to sample at an adequate scale, and that's the issue. We've just been scratching the surface up till now. And that's shown here in that our first instrument which did this at all is SkyMatchy, which flies on the ENVISAT mission of ESA, which is still up there, but decided to switch itself off at 2012. We're still hoping that it might wake up again, at least some of us. I don't think it will. But you can see that on the scale of something like Berlin, this is the city scale, that we have actually only the whole of Berlin, so we have 1 point. Now we know that the sources are a lot smaller than that, so GOSAT, which came along next from JAXA, has a spot size, which is shown there about 85 square kilometers at the end of the day. And then OCO2, which we saw some great data from, which is of the order of, should we say, 4 square kilometers, 3 square kilometers, which is much better, but it's got a very narrow swath. And the microcarb, which is planned, is sort of similar. And what we want is based on our carbon-sat development, which we did with OHB and the state of Bremen and also eventually ESA. We want, and this is now being considered for Copernicus, and you can see the density of measurements, and we want this globally, so we'd like to have a constellation. Now the reason, of course, why we're doing this is, of course, just remember that CO2 is the largest driver for climate change, okay, and followed by methane. And this is the type of data we already have, and we've seen this nice breathing of the Earth. When you take April and September in 2 different years, you can see that the northern latitudes, by using photosynthesis and the building or growing of leaves, basically takes up this, and that's why it goes sharply down from May to September, and then the leaves fall, and then they release CO2. So at the beginning of the year, we're making CO2, and we see this dogleg, basically, or sawtooth approach over the years. And this is now all satellite data combining Sayamaki and Tanzo. Okay, and we see the same behavior repeated. But what we really want to see is the emissions. And here, just for an example, we did an experiment with ESA and NASA funding, and we flew our aircraft instrument over the Central Valley of California, which has lots of different sources. Oil wells, kind of fracking type of stuff, and of course cows, and we were able to identify each of them, but it's very complicated, and that's why we need much higher resolution in the future. Now, with the planned satellites, even the new best ones, this is the picture that you'd get Okay, that's the high resolution, which is 50 by 50 meters aircraft. This is what you get when you do 7 by 7, and that's where we're at the moment. What we want is 1 by 1. So Michael and the other agencies, we need a lot more and better in the future. This is a challenge for everybody. And one of the ways forward is maybe, yes, actually, and this is one way forward we're thinking about is going to small satellites and swarms at the end of the day. This might be a 2040 or 2050 solution. Okay, just to say we are pleased with the new results from CH4 from this Sentinel-5 precursor. This is just taking some nice pictures of India, and this is a single day's data, more or less, one of the first measurements. So this is beginning to work up, and you can see where the population, this is a mixture of emissions from people and rice growing, primarily, if you look at that picture of India. And we see that day-to-day changes. I'd just like to point out, one of the things that we found out was that the CO2, it's a controversial result, but we think that the CO2 sink in Europe is larger. And this goes back to, I think, the perfect measurements made sparsely give the wrong data. When we do hemispheric averages, it agrees. But when we do local, separate it, we see differences. Okay, the vision for the future is, as I say, we go from the big satellites to do things in a small way, and that's a challenge for the engineers. Okay, thank you very much.
Thanks, John. Yeah, we see we need more information, so we need more measurements, possibly in the future also on the dark side of in the dark, you know, with active laser radar systems and so on, to really get this very complex mechanism of climate change better characterized. And in that sense, I'd like to switch a little bit to the young generation. And here, Audrey, I mean, you're working in Scotland at the moment, so it's probably not a climate change being felt in Scotland, but you were working also for ESTEC in the past. I mean, do you have a feeling this is really developing now? I mean, the things you worked on probably a couple of years ago, are they now more major? Are they improving? Is this the right direction, or what is your view in this direction?
I'm not sure if it's on. Yeah, okay, thank you, Timo, for your question. But do you want me to give a ESTEC perspective or more of my perspective in general on climate change in general? Okay, so first of all, I'd like to cite Joseph Albasher, he's our Earth Observation Director, said this morning that there is no planet B. So I guess all of us as citizens on Earth, we're on the same boat, so we should all be very concerned by climate change, not only in Scotland, actually. Second of all, us in the space field, we have an additional responsibility because we know that a lot of climate change variables can be observed from space. And actually, there is this study from the European GNSS agency and UNOSA that showed that 40% of the UN Sustainable Development Goals, the SDGs, can be positively impacted by space-based measurement. And finally, so I'm doing my PhD in AI, for space mission design. So I'm at the start, let's say, of a spacecraft life cycle, but I really believe that there are many exciting opportunities for AI to help with downstream application, and especially, for instance, unsupervised learning to help us deal with the terabytes of information that we are getting from space. So obviously, I'm not I'm not a climate change expert, but I hope that today's discussion, we can discuss about what are maybe the current obstacles for us to fight against climate change, whether it's maybe more technological, so are we missing some models, are we missing some instruments, or if it's also more of a political issues that we are not managing to enforce climate change policies.
Okay, thank you. Good, and Charlotte, I mean, you did your PhD, and now you changed into industry. I mean, is there, what is this move also a little bit in the sense of working on the Copernicus program? I mean, it's not the atmospheric issue, but it's a Copernicus program. That's the right move for you?
First of all, thank you for allowing me to be here on the panel. I'm very awed to be here, sitting between people who have had years, many years, investigating this super important issue. I have years of worrying about it as a person, but I haven't really, I'm like Audrey, I have not been long in this area. I'm a system engineer working on Copernicus expansion currently. You mentioned one of them, the CO2 monitoring mission, but I'm actually working on land surface temperature mission, which is not like what we have seen here a lot, and also in the earlier panel a lot, about measuring the causes and effects of climate change, but actually try and mitigate some of the consequences. With LSTM, we will be able to determine soil moisture levels, and that should help most effective water use worldwide for agriculture, and also in that way to combat the growing food insecurity that comes with desertification. So my perspective on it is, of course, yes, we need to stop climate change. We need to be able to accurately measure it and see and understand the phenomenon better. But also, we as a space industry can maybe help deal with some of the aspects that cannot be changed or cannot be stopped anymore.
Okay, thank you. I mean, we saw it's a complex matter, this whole process. I once read an article that it's like a little bit sailing in the darkness, and we have some spots of light and some understanding, but no one can exclude that we reach a point where suddenly an avalanche is happening. So that suddenly, we know about the permafrost and the methane coming out, and that suddenly some processes are interacting like an interference, a positive interference, and bringing really a dramatic change, not this continuous, but a really dramatic and exponential change. Is this something you would be also afraid of? I mean, I'm just giving it to the panel in general. I mean, do you think this can happen?
I'll grab the word again, because this really reminds me of the Kessler syndrome in space debris as well. I've also spent some years looking into space debris, and we have the same effect. Up to a certain point, we can accept that there will be space debris, but that at some point there is a cascade where the satellites crash into each other, and there is a point of no return. And we have a similar problem, I think, in the space debris world, where you wonder, there are some ways we could stop this, good laws on how to design spacecraft and how to decommission them after the end of their life, and also maybe active debris removal missions to get rid of some of the worst dangerous objects, but always the issue of how to convince somebody to actually pay for this and actually, how to actually realize it.
If I could just make a comment, I think that's a good parallel, actually, because the Earth system is a really complex, non-linear system. And for example, nobody predicted the ozone hole. I was working on problems to do with ozone removal in the laboratory at the time, and nobody predicted the ozone hole because in the models, non-linearity. And this is an issue also for artificial intelligence and machine learning. You only learn from what you know, and the problem is the system can change. And this is one of the reasons why we need the measurements, okay? And we need fit-for-purpose measurements, which means measuring in time and space adequately. It's essentially first semester physics, okay? But that's the point, and it's being prepared for nonlinearity. Now, just to kick in a big issue on this, in the short term, it's the land surface, which is in CO2, for example, the big problem, probably also in methane. The ocean, in both cases, probably has a much longer time constant. But at this moment in time in Korea, the IPCC people are talking about, can we hold to, or could we hold to a 1.5 degree rise, accepting that we've probably already got a 1 degree rise. And the issue is all about switching the CO2 off early enough, okay? It's a question of hysteresis. The system has significant hysteresis, so if we don't get out of fossil fuels fast enough, we will, just not make it in any kind of adequate way. And I'll just make a personal point, is that my house is at 7 meters above sea level. So I'm okay for Greenland. Michael was showing very nicely about increasing sea level, which is mainly expansion at the moment. But sea level, when I was a young fellow, Greenland would go, people thought maybe 400 years, something like that. Now we're talking about 25 because we didn't understand the mechanisms. And that's a big issue. So that a lot of, the point is timeliness. And I think the space world has to get on top of this and give the measurements that people need. Maybe Michael.
Yeah, so I was actually going to start at the same place that John did with the nonlinearity. We are discovering many positive feedbacks around the present climate state. Understanding those processes in detail is absolutely necessary for predicting in the near term what things are going to happen. You know, the melting of the sea ice, for instance, also changes the albedo in a negative sort of way, leading to a positive feedback system. But once we understand the real processes, and it's incredibly difficult when biology is involved, then we can start to predict how those processes will take greater or lesser weight in a significantly different climate state. It's not a small perturbation from where we are now, but one that is really quite qualitatively perhaps different. That sort of understanding, which is going to be driven by measurements of the present state, but also is going to be driven by good theory and good scientific analysis to really get the processes quantified is going to be absolutely necessary.
Yes, please.
Can just add one more thing to jump also on what John said. So just a side out, I live in the Netherlands at the moment, so I'm also worried about sea levels rising.
More worrying.
But they can help us deal with that. Also just about machine learning and so on. So just wanted to add that maybe the way we can see it is you have different level of mitigation. So you have long-term mitigation, so measurement, but we're also going to need very short-term mitigation actions. And we see that there are more and more intense meteorological events, so that due to climate change, and probably believes that the autonomy, AI can provide autonomy, maybe in constellation, to increase the responsiveness that we are going to need during disaster monitoring.
I'll just come back and then give that with Michael, but quickly, yeah, I completely agree with you. We need here multinational, multi-scientific attack on this problem at all sorts of different scales. And you know, it's a key problem that we use all of the potential, but we have to recognize also to get the structures into place so that we can eventually manage the change as we approach 10 billion. And that's a key issue, and we're going to need all these skill sets and a lot more. And some years ago, I did a back-of-the-envelope calculation which said if you put a 0.1% tax on a barrel of oil equivalent, okay, you would have, and you would never notice this at the petrol or gas pump, for my American friend here, if you put this tax on it, you would nobody would see it, but you would raise so much money if it was directed to a space and ground-based system for measuring and delivering a monitoring system. You wouldn't know where to spend the money. OHB would be laughing all the way home.
So, of course, there would be other people who have other ideas about how to spend the money, and therein lies the problem. But John brought up the ozone hole issue. It is both very positive in my mind and quite sobering from a scientific standpoint. The nations got together in '87 eventually with the Montreal Protocols, and we did as a species change what we were doing. And indeed, the spaceborne measurements and others are showing that, in fact, with the hysteresis and everything, the ozone concentrations are doing what we expected on the basis of Montreal, and that by the 2050 or 2070 time frame, the stratospheric ozone levels will be back down to what they were when dinosaurs roamed the earth and John and I were in elementary cave. The sobering part from a scientific standpoint and from communicating with the public is that probably the largest uncertainty in climate prediction is not the lack of knowledge right now of processes, et cetera. I'm going back on what I said before, but is the fact that the biggest influence on the future climate is probably going to be what humans decide to do as a society. Convincing the general population that making the models better, which is really necessary from a scientific standpoint, might not improve the accuracy of the actual forecast. It'll improve the projection, but not the forecast, is really important, because the forecast accuracy depends on what society decides to do, a different view of uncertainty.
Actually, I have a question there. You mentioned this also yesterday in the panel discussion. The biggest uncertainty in the simulations is the human. And somebody raised the issue of big data in that discussion. And that got me thinking. I wonder if maybe in, in a few years or so, it would be possible to get some sort of prediction that can feed into these models that comes from big data and that allows us to predict a little bit better how policy would react to certain events? Or do you think that is impossible because the human is just too unpredictable?
Honestly, I was not swayed by that argument. Humans as a group are, the argument that came up yesterday that was presented was that there are companies like Facebook and Google and everything, which are making a lot of money out of somehow doing statistical analyses and predicting and therefore capitalizing on individual choices that humans make. But those are choices that revolve around the individual and around consumption mostly, as opposed to choices that revolve around philosophy and policy. And that's where I'm quite skeptical. On the other hand, I really don't understand people.
Yeah. Let me just briefly say one thing, coming back to this ozone hole. I think that was the nice thing, that there was one, it could be identified what was responsible for it. And then I think everyone stands together and say, okay, we ban this stuff and don't release it anymore in the atmosphere, and then the things get better. I think on the climate side, it's more difficult. It's really more difficult because the effects and the correlations are much more together. And the things you just showed this morning on, the effects of the 3 different wood areas, in South America, in Africa, and in Indonesia, in the Asian area. That's really something we just learned on this one. And there's surely much more of this type of correlation. So that's just a short remark from my side.
I just wanted to jump a bit back on what you just said about the future being decided by society. I was wondering if maybe our future is unfortunately more decided by politicians, because in 2015 we had the COP21 in Paris and everybody was very excited about all the engagement. But then in June 2017, President Trump decided to withdraw from his agreement. And then my president...
My eternal embarrassment. Please don't.
So my president, Emmanuel Macron, offered to the American scientists to come over to France. I mean, it's a nice place, a good country, but in any case, a bit of advertisement. In any case, I was wondering, do you think actually we're gonna, because we have a technology, we have good scientists, but does it really matter in the end if we don't have a political support? And how do we bypass that?
Well, it's not a question of bypassing, it's a question of influencing. Look, the politicians and the institutions that we have are us. They are the integrated result of decades or longer of human history and Western civilization in this sense. We have communication issues when we are talking about events that might happen generations in the future, but that we can influence now. We don't really understand very well how to get that across to the vast majority of people, how to appeal to them. The politicians, frankly, I don't view them as, well, I view some as evil, like our president, but please don't write that down. I mean, they're not evil. They are reflecting something about the societies and the areas that they represent. What we have to do is to come up with very clear and understandable arguments about what is happening and what its effect will be. We have to repeat those arguments and those points endlessly, and they have to be articulated by trusted spokespeople. That virtuous combination over long periods of time, there's not going to be an epiphany that happens, but over long periods of time, that may change society's thinking, and that will then be reflected perhaps in the political representatives and the institutions that they establish.
I think you've got to remember also that I would say this, that something like 60% of the climate change research is actually going on in the USA at this moment in time. So we in Europe should actually start doing something actually here to help out a bit, and the rest of the world, by the way. But I think that the issue is, Michael has explained it very eloquently. The issue is maybe really about human nature. That's the problem. Human nature has a good sides to it and bad sides to it, but this is an issue that for our grandchildren and great-grandchildren is potentially catastrophic. We have had species going out, they call this biological catastrophes, in the past for all sorts of reasons, and we may well do ourselves in. So what we can do as physicists is, and chemists and biologists, is to provide the data and keep, as Michael said, putting the message forward and trying to provide the information that's needed for policymakers to develop the right approaches. And for this, we need a multinational approach. So I'm absolutely behind these things, personally. But I think what we can do, there's an expression in German which says Schuster bleib an dein Leister, which means shoemaker, stay on your shoemaking machine. Okay, so I think we as physicists, we can't become talk show hosts or the rest of it. We do have to breach into this area to be better, and there's a growing policy group of scientists who are coming from a good physical background, but I think there's a role for as I said before, we need all our skill set to solve this problem. But don't stop the measurements, for God's sake.
No. The three parts of the virtuous trinity that I mentioned, one of them is the argument delivered by trusted sources. So we as scientists are not all well equipped to do that communication, but we may be well equipped to communicate with and educate other trusted sources, TV meteorologists, for instance, and others. And they can then take on a lot of the role of the general education.
Very good, yes. I'm just looking to the audience. I don't know if you have some urgent question, then, okay, so I'm happy to offer you a mic. If maybe there are two more over there. So, please. So this is the young generation. If there would be older people always sitting in here, there would be questions. No, but here 10 fingers. Great.
This question is pretty much for anyone who has a relevant experience, but what are the biggest challenges you face with constrictions set by administrations that might have other interests in communicating or public outreach of changing the minds Michael, like you were saying, actually engaging the public about what the actual science is and people who may have an interest in smearing that truth.
There's one Michael on the floor.
Yeah,
Mike?
one Michael and one nation that's, I guess two nations are now not part of COP21 anyway, or have expressed that. Let me speak, first of all, quite honestly, for NASA. And that is that although there is much Sturm und Drang, a lot of discussions about constricting science and earth science communications and everything, we definitively have not seen that in NASA. And indeed, our new administrator, Jim Bridenstine, who was a congressman, a politician, who had expressed some skepticism previously about the changing climate. By the way, I never say climate change, or I try not to. That polls very, very badly as a litmus test, but everybody agrees changing climate, that's something that they know about. In any event, Bridenstine, when he was a congressman, was quite skeptical. As NASA administrator, he has taken every opportunity, including here, to basically make 3 points. One of them is that, yes, he agrees that the climate and our environment are changing, that yes, humans are playing an important role in it, and that it is part of NASA's mandate to actually measure and understand that. We couldn't frankly ask for much more under the circumstances in an agency. I would not be the Earth Science Director for ethical reasons if there was censorship or anything like that that's going on. One of the jobs that I have is to keep our community focused on doing the work that we know we have to do. We have a budget, we have a plan. Nobody has told us not to spend the budget to advance the plan. And yet, many scientists, many investigators are going, oh, I'm so worried about what's going to happen in the future that I can't concentrate at work now. Okay, that's pretty much a positive feedback system in a bad way also. Everything that we learn is truth, and having those accomplishments just builds our credibility. There are other aspects of the US and the administration, obviously other agencies, mostly having to do with more regulatory aspects of things, where the political impact of the administration is being felt significantly more to an intolerable level, I would personally say. But that's not true with NASA.
Okay, thank you. You want to say something?
I'd like to come in on this. One of the very good things that was done in the creation of NASA in 1958, there was a precursor called NACA. One of the very good things was it gave NASA not just a mandate. In law, NASA has to do science.
Space Act.
Space, yeah.
And protecting the Earth.
Yeah. And so every administrator can say to the Congress and President, we have to fulfill this law. Now, you can change the laws, but that's a tremendous thing. Now, I'd like to see that for Europe and for Germany's space, because it can be, in Europe, I would say, we're pushed towards commercialization, and commercialization is not very interested in climate change or changing climate, to use the right word, in the short term. Maybe in the longer term, as the services, we're trying to push it in terms of services as a way to do it. But I think there are some sort of inalienable measurements that have to be made in this sense, and it's public. We're basically, a lot of us on this side of the table are public servants who are trying to provide public information. And industry key issue of industry is to deliver it. Now, services are a good way, and commercialization is a good thing. It works very well in some areas, but bad news is not something you often want to buy. So that's why we need also in Europe a system like the NASA system, which delivers also the bad news hopefully in a nice way, in a pleasant way, to get it across. And there was a question about the issue. I think that of course people are depressed by bad news when it comes to funding and this sort of thing in general. But we have to keep fighting. We can change it. We are the people who elect people. We're also the people who change things. We're part of that system.
Okay, thank you. So I would like to take one more question from the audience, and then Audrey. I think that's the point. So one more urgent question, please.
Good morning, Michel Tosser from ISA. I like very much your discussions, and they're very valuable. I had a dual stage question, in fact. Mr. Burrows was mentioning that we need actually more temporal and spatial resolution on the CO2 measurements by the new ESA Copernicus missions and so on. And he showed the example of the aircraft flying over Texas or so, where you saw the emissions from the cattle and from the cities and so on. So the first question was, how do you see this in the future? How does it work to say, okay, you are expelling too much CO2, you should give your cattle less food, or you should stop driving your car? So this is one question. And I'm a bit skeptical about this, because actually we already know what is the problem. Yeah, you see the numerous organizations like 350.org and so on, advocating a fossil-free environment and society. So the second question, and I'm coming back also to your shoemaker example, we are basically in the space domain here observing the problem, yeah, and that's very good and necessary. I don't discuss that. But what are we doing to actually, which action are we taking? And I'm wondering whether there are any means that we could do from space to actually diminish the number of the amount of CO2 or whatever. We have seen things like space shields or sun shields and ideas to release sulfur dioxide into your atmosphere and things like that. But are we exhaustive on these ideas? And maybe can we do more from that side, from space, to actually take action? So thank you for these two answers.
I'm happy to have a go. Yes. I'll have a go, and then maybe Michael, and then my colleagues here. Okay, geoengineering, which is what you're talking about. My former boss, Paul Crutzen, put this out as being, we have to think about these things because if we can't stop the CO2, what can we do? And that's putting up SO2 or little particles to try and prevent the amount of sunlight coming to the Earth. These are tough challenges. In the short term, you can do the so-called short-lived climate pollutants. You can get methane down. You can do aerosol, change get the absorbing aerosols down. There's a bunch of stuff that we can do in the short term, okay? But the CO2 issue is a longer-term issue, and that definitely has to be dealt with. Generally speaking, the geoengineering studies tend to have also side effects. You have more sulfuric acid if you put more H2SO4 up. This has other issues. So when you're playing with a very complicated system, it's difficult. The best thing is to get out of CO2. I have to say Germany has decided to move to more wind and related energies. Europe's moving in this direction. The big thing is to get out of fossil fuel combustion and to start looking at ways you've got opportunities to dump biomass. You can make biochar. There are a whole host of things. You can't do that from space. It's other people who are doing that. But space is required to follow it, because you need the global picture and you need to see who are the bad guys. Basically, you have to shame people into doing it and show. Now, we have a good example of this, not just in the ozone hole, but in the NO2. We measured from GOEM, NO2 over China, and I got letters saying you're some kind of British colonialist who's trying to tell that you should still own us or something. And we were just showing that it's going up. My colleagues here in my group got this data. It was very interesting. It's really going up rapidly. And now China has gone over the top and is bringing it down. And they've reduced NO2. It's still massive. If you go there and get off a plane, you can smell the pollution, which is another big issue for us, kills 7 million people a year. But they're doing something about it. So you can do things, and it's the provision of the knowledge that provides it. And that's what space does. And that's why we need to do it. Obviously, there are policy maker parts of the science world, or policy science overlap, and that's fantastic. But I remain as a Schuster, and I'm trying to make better measurements.
Thank you.
I would like to say just a few sentences about space-based geoengineering. The research lab where I was working was actually one of the projects I was also working on was space-based geoengineering. That was far out stuff. We were looking at capturing an asteroid, mining asteroid dust to create some sort of sun shield, and or floating mirrors and so on, all of these different things. But one thing they all had in common, I mean, apart from being very, very expensive and and not very feasible, is that once they are gone, you actually have some sort of knockback effect, and you have rapid increase in surface temperatures. And this means either you have to commit and you have to continue this for hundreds of years in the future, or you're just delaying your problem, and then you have something hitting you with the force of all that you've been spared in the meantime. So that's why I'm very skeptical about space-based geoengineering.
Okay, so Michael, you.
Yes, with respect to geoengineering, I also am exceedingly skeptical and agree with John and Charlotte. The Earth is an incredibly complex system. John talked about unanticipated consequences, but it takes a level of hubris that is, arrogance, it seems to me, for us to think that we know enough about the feedback systems to be able to predict with any level of confidence what major geoengineering approaches will have on any time scale. And the consequences of making a wrong decision are huge, given our populations that live in environmentally sensitive places. 100 years from now, perhaps a panel will be talking differently. I don't think we're close to that now. I'll say a word about the commercial sector from a different sort of point of view. And I actually learned this from talking to a whole variety of people in Europe over the decades about commercialization. And the private sector's interest in the environment. And it's really interesting because it has a result that I hadn't anticipated. There is a strong feeling among environmentally sensitive industries that the government should probably stay away, because they believe that there is money to be made in, as I say, in going green, in environmentally sensitive practices. And the last thing that they actually want is for the government to have a rising tide, no pun intended, that lifts all ships, when they can use their superior knowledge to actually make money and do good as well. That was a real eye-opener, talking to board members in large businesses and reinsurance people.
Okay, thank you.
I'll just give one example of that. There was AccuWeather predicted a typhoon, hurricane, or a local one, a tornado actually, and they released it to the people who bought the knowledge, but not to the local citizens. And that's the problem. That worries the line. Okay, it's good that the people were buying it for their interest. They shut down their industries, saved their plants, blah, 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 blah. But actually, few people died. And that's just a small tornado. And then if you think about big hazardous weather, it's a big issue. Michael's raised a very interesting point.
Can I just add something? Because with Charlotte, we wanted to tackle a bit the idea of commercialization into climate change, and maybe it's good if changing climate can be less of a bundle of bad news, but can become an economical opportunity than to develop a new ecosystem. And for instance, an example that is out of a space business, but there is this bank called Plastic Banks that has started to create, to use plastic as a currency. So you're transforming like waste, something, kind of bad, into a currency. So if you could have something similar in space, maybe it would, help us. It would create a new momentum to fight against changing climate.
Yes, where the money goes, I mean, that can be surely a driver in that sense.
If bad papers could be turned into currency, I'd be a rich man.
Okay, so yes, time rushes a little bit. So I would like to end this discussion. I don't want to end it, but I want it. There's a question, but the problem is that our time is maybe nearly, therefore I said two questions in the audience, and there were three at the end because there was one double question. Okay, if you have a very quick one, maybe please go ahead, a very quick one.
Yeah, greetings, Bill Nye from the Planetary Society. I am fascinated by the idea of reflecting sunlight from the sea surface. So this would be understanding how much sunlight is reflected from the surface during storms, where the introduction of bubbles into the ocean makes the surface whiter. In English, we have the expression white water, and white caps are ocean waves that turn white. And I've often wondered if it would be possible to artificially introduce so-called hydrosols, air bubbles, on the backs of big ships, so that this would be helping to reflect sunlight into space. But as I watched like the second or third graph, I got the impression that we don't understand sea surface reflection well enough to even consider this. I wondered if you all had looked into ocean reflectance changing with storms.
You take a fast answer?
I think that this is a more detailed thing, but I can say that we calculate these things. There's a famous paper called Cox and Monks from 1955, which addresses how you calculate the albedo. But I think, you know, I think I would just say the idea of creating lots of white caps or white water, particularly by using surfactants, would have a lot of interesting other effects. Okay, for the biosphere that lives close to the surface and is interacted by it. So I think, again, those are sort of things that need studies to be able to assess the biological impacts of those things and any other impacts. Anyway, that's just my personal view.
Okay. So thank you very much to my panelists that we had this interesting discussion here. But I would like to end it with for each of one of you giving a statement. And I mean, what do you take out of here? What is your view to the future? I mean, please, Audrey, you might start in 2 or 3 sentences in that sense.
No, thank you very much for this conversation. I think I learned a lot personally. There's just one more point that, well, we didn't have time to tackle. Maybe it was international cooperation and the importance of involving everyone, including emerging countries. But maybe we can continue this conversation later on.
Michael.
Again, John and my generation has given you tremendous challenges and opportunities to excel. The problems are really complex, but the impacts are easy to see, and the potential benefit that your science can provide in terms of societal benefit and improving the lives of each person on this planet are huge. This is the field to be in if you want to have leverage on the future of our species.
For me, working in future missions at OHB is exciting in and of itself, but knowing that what we're working on currently, which is the expansion next generation of the Copernicus satellites, has such an important contribution to helping understand this phenomenon and maybe helping offset some of the consequences, makes it even more important, and I feel very, very lucky that I can work in this area.
Okay. John?
Well, it's been a great honor for me to take part in this panel. I am encouraged by the questions and encouraged by the discussion. Changing climate in this, what we now call the new geological epoch, the Anthropocene, another idea from Crutzen. This is the challenge of the century, and it's up to the younger and not so young members of the audience to solve it. I'm encouraged. I actually think when you go around schools, when you go to younger people, the message is there. also in the developing world, the message is there. The question is how we do it, but that's a challenge, as all political issues are a challenge. But I'm optimistic, and if we continue to provide the evidence and make it so convincing, even more convincing, I'm optimistic. Basically, scientists have to be optimistic. We're optimistic by nature because most of the time our experiments don't work. So, you know, this is a soluble problem, people. Go do it.
Yes, thanks. And from my side, not as a moderator, but as personal, I take it with the word of Macron. There's no planet B. There's only one planet A, and the other planets are potential extraterrestrial planets are very, very far away, and they're not nice. So we really have to solve this issue. Thank you very much to the audience, and thanks again to the panel. Thank you very much.